Hey everyone, welcome back. Today we're going to be taking a look at a new topic that I'm pretty excited about, and that's Gray-Scott reaction-diffusion patterns in TouchDesigner. So as you can see, this is one of the systems we're going to be working on today. This is one of the main kind of quintessential reaction-diffusion systems, and that's what we're going to be building. But before we jump into that, I want to show a little bit of motivation for kind of why we're doing this and some of the cooler things we can make using these techniques. Here's a little video that I created using this technique earlier this week. Here's a couple other examples. This one obviously is similar but with a different colorway. This dynamic is pretty interesting. I really like it. There's a lot going on, but you can still kind of somehow grab all the different pieces. And this example is another I like that looks a little bit more like something you would see under a microscope, I think. So I wanted to show you kind of these a little bit more advanced works at the beginning so that there's some idea of where we're heading and the level of complexity and composition you can get with these techniques. So with that being said, let's go back to what we're actually going to be working on today, and that is this simple Gray-Scott reaction-diffusion talks. Now I will note that this is going to be a multiple step tutorial. I'm going to show you today what we're looking at, and so you will be able to do kind of what we're seeing in front of us by the end of this tutorial. And then in subsequent tutorials, I'm going to go over how to add a preset system for this type of reaction diffusion talks. And beyond that, we're going to, in part 3, go through some of the more advanced topics that can lead to getting some more interesting type of dynamics that look closer to what I'm showing you here. So, with that said, we do need to start at the beginning, and that is going to be with this reaction diffusion process. Now, before we even jump into TouchDesigner, I do want to look at a little bit of resources on the internet and understand just kind of what we're talking about a little bit better. So, the first thing is just the reaction diffusion model, and for that, I'm going to look at this website. I'll link this in the YouTube description. So, what are we actually talking about when we say reaction diffusion? And, like, what is it, I guess? So, to take a step back, reaction diffusion is going to be a series of equations. And those equations are going to represent a chemical reaction. Now, the chemical reaction can be between any substances, and the substances and kind of form of reaction are going to take a little bit of a different flavor depending on some of our choices for parameters, implementation, and also what actual equations we end up using. As far as the equations I'm going to be using right now in this tutorial, those are going to be these Gray-Scott equations, as I've mentioned several times, but it is worth noting that those are only one set of a system of reaction diffusion equations. So we're going to go through this step-by-step process, but you will be able to use the techniques to implement your own using equations that may be derived from a different model of reaction, and that's pretty exciting too. So first things first, let's just kind of jump into these chemical reaction equations and understand a little bit about what we're talking about. Now, for that, there is another page, and this I'm going to also link. It's going to be Carl Sims' tutorial on reaction diffusion. So both of these are really nice resources, and I recommend reading through both of them in full before you go through the rest of this video. It's going to really help having some good conceptual and mathematical basis for what's actually going on here. So, if we start with this reaction diffusion tutorial from Carl Sims, this first box is really most of the conceptual basis, and essentially what we're seeing here is that we have chemical A and chemical B, and our diffusion equations and our reaction equations are going to define how those two things are operated on. And so basically we're going to say if there are two B's and an A, then those three, let's say, molecules are going to undergo a transformation where the A molecule actually converts to a B molecule. So B is using A as food to grow and evolve over time. We then have another parameter called a kill rate, and that is to ensure that we don't have too much of chemical B at any given point in our reaction simulation, because that would lead to instability, and we would basically just have a land full of B with no A, therefore no reaction diffusion. So this is the reaction where two B's take an A, convert it to food, and then essentially make a B out of it. The diffusion part of our system is basically just how these chemicals spread out over the simulation environment over time. Now, diffusion is very simple, it's very common. You can think about things like if you have a very hot piece of metal and you put it on, let's say, a metal tabletop, the tabletop around that metal is going to get hot because the heat diffuses from the hot piece of metal onto the metal tabletop. The rate of diffusion determines how fast that heat in this example spreads, and the rate of diffusion is a parameter that's determined by the substances that we're using and the environment that they are situated in. So for our purposes here, we're going to just make some assumptions on what those values are for the diffusion rates, how fast our chemicals are going to diffuse. And by doing so, we're going to be able to kind of have this reaction that's occurring every frame, let's say. And at every frame as well, we're going to take the chemicals that are left and spread them out a bit and just kind of diffuse or percolate or propagate those chemicals across our reaction diffusion simulation environment. And in the process of doing that, more molecules that wouldn't otherwise have been able to interact with each other and therefore react will, because each step we are spreading those chemicals around and we're kind of just forcing that reaction via the diffusion. And so you can think of it as the diffusion process is kind of the one that is supporting the reaction and allowing the reaction to happen by ensuring that those chemicals are evenly, if not linearly, spread across the reaction diffusion environment, meaning that they touch each other, and then we have our reaction. Now, that's a little bit maybe difficult to think about without a nice visual example, so let's take a look at this WebGL Explorer, and again, I'm going to link all of this stuff, so don't worry about it. If I re-init this, and maybe we'll take a different one. So we can see that as I'm kind of like drawing with my mouse, which we will add in our system as well, and then maybe change these settings, there's different dynamics that appear based on what settings I choose, and we can see that gradually, even if we start with something small, based on the parameters, that pattern will diffuse and kind of grow to fill the entire reaction diffusion simulation. We can use these parameters, like I said, the feed rate and the kill rate, to determine the reaction form and pattern. And these are essentially the weights that are applied to this reaction process, and that will be the number of new chemical A molecules that are added to our reaction. Let's think about it as each frame. And then the kill rate will be the number of molecules that are removed from chemical B each frame. Now, these numbers are not going to be represented as numbers of molecules, but rather as concentrations that are a float value between 0 and 1. So because of that diffusion, we're seeing these reactions propagate, and that is what we're interested in, and the cool part. But how? How does this all work? And for that, we're going to return to the tutorial. So this somewhat heady-looking set of equations is going to be how we calculate what reaction is occurring at each time, at each pixel of our simulation. So before I jump into this, which is well explained, but a little bit dense, I'm going to go back to the not very much less dense equation on this tutorial, or really just website from MIT. The reason I want to go here is because what we're really looking at when we talk about any of these systems are systems or series of partial differential equations. In most cases, they can be ordinary differential equations in specific cases, but more generally partial differential equations that describe how the system reacts over time. The entire point of a differential equation, and really what a differential equation is, are sets of equations that are telling us how over time different measures of interest, quantities of interest, rates of change, whatever you like it to be, are measures of interest change over time based on some parameters. And so what we can do is take these differential equations, we can use the principles of mathematics to find a numerical approximation at the solution of these differential equations. And using that numerical approximation at the solution of the system of equations, we can actually produce a physically realistic simulation of the equations, which is to say we can simulate this chemical reaction using a numerical solution to these partial differential equations, which sounds a lot crazier than it actually is. We can see right here, one may expect good results with even such crude methods as forward Euler integration of the finite differences equations that one obtains by spatial discretion of the Laplacian. Now, that sounds like a lot of words. There are some big words in there, and for those of you that aren't mathematically inclined, you're probably thinking it's time to run away. But the implementation of a forward Euler integration of the finite differences equations that one obtains by spatial discretion of the Laplacian is easier than it sounds, and so that I don't need to go through the math for you and probably bore everyone and definitely scare everybody away. Now that we kind of understand what partial differential equations are and how they can be used in this context, we can go back to the Carl Sims tutorial and we can look at his system of equations. Now you'll notice these are quite similar to the partial differential equations. Let's get both of these up at once. This term in the partial differential equation we have on the left side our partial u partial t, partial v partial t. This is basically saying the incremental change in u or v, which is the concentration of A and B respectively. The change of each of those concentrations at a given time step can be calculated by this right-hand side of the equation, and that would be the Ru, that's going to be a diffusion constant for our chemical A. This upside down triangle with the superscript 2 is actually a Laplacian operator, so we'll talk about that in a second. U is in this case our concentration of our chemical A. So U will be A and V will be B. Minus, we have this term, which is concentration of A times the concentration of B squared, plus the feed rate times 1 minus the concentration of A. Similarly, in our partial V equation, we have the diffusion constant for B. We have the Laplacian, the component of the Laplacian for the concentration of B. That's going to be our diffusion term, which we'll talk about in a second. And then here we're adding that same term, which is the concentration of A times the square of concentration B. And here we're subtracting the sum of the feed plus kill rate times the concentration of B. And so that's very, very similar to what we have over here, but there are some important differences. On the right-hand side of the equation, we have A prime and B prime instead of partial U, partial T, and that's a hint that this version of the equations is actually a discretion of the other set of equations over here. And what further gives us that impression is that we have a term on the right-hand side of these equations that we didn't have at all on this side, and that is this A and B. So what this is really saying is, on the right-hand side of these equations, which are on the left, we have our current value of A, and then we're going to add one time slice of this entire partial differential equation, partial U, partial T, to our current value of A to get the future value of A. And so what Carl Sims' tutorial set of equations are saying is, okay, we can actually use the differential equation with a very small delta t, exactly one time slice. We can take the value that we have now, our initial value, we can use one time slice of the partial differential equation to understand what the finite difference is between our current frame value, our initial condition, A, and our next frame value, our calculated condition, A prime. So what Carl Sims is doing is exactly that finite differences form of these partial differential equations that we can also consider a forward Euler integration. And what that means is, basically, we can just code these equations as they stand in a shader and use that to simulate this system. So now I'm going to focus just on these equations. And you can see that he has a lot of really nice annotation, which is why I want to go through this so exhaustively. So we have A prime, B prime as our new values on the left side, like I said. We have A and B as our previous values. Now this dA and dB are diffusion rate constants for A and B. So those are just scalars that will be multiplying. Then we have our upside down triangle with the superscript 2. That's a Laplacian operator. I'm going to talk about what the Laplacian operator is in just a second. But for right now, that's the Laplacian operator. So we'll take the A component of the Laplacian and the B component of the Laplacian. Now we have our reaction step. And so this is, remember from up here, how two B's take an A and convert that to three B's. So we have our reaction step, which is the chance that one A and two B's will become three B's. Because A is converted to B, this amount is subtracted from the A concentration and added to the B concentration. And we can see that right there. Now in the A, we have a feed parameter, and so we'll be scaling our A concentration by the feed constant. And then we have this 1 minus A term to make sure that our A doesn't get too high, because our concentration is supposed to be between 0 and 1. And then on the B equation, we have our kill term, and so we're basically subtracting the feed plus kill, because in that sense, you are adding to the B from the A as part of the reaction, and so you want to remove that from the B, and then you also want to kill some of the B otherwise, so that we have room for the reaction to grow. Now we scale this term by B so that it doesn't go below 0, and then our very last term in both equations is the delta t, and that is the finite difference in time between frames in our simulation, and that is basically what allows us to use this form of equations and add this calculated term to our prior value to get our new value. So, I hope that that was helpful and kind of demystifies a little bit about partial differential equations overall, and also how we can think about taking partial differential equations and converting them into a form that we can use through parallel computation, such as shaders in TouchDesigner. So now that we've kind of talked about the mathematical basis and the conceptual basis for reaction diffusion and looking at these equations, at this point it probably makes sense to actually try and implement some of this stuff in TouchDesigner. Although, I realize that before I do that, I do need to talk about the Laplacian, because the Laplacian is a very important part of this reaction. So where's my other, here we go. So where are, oh, oops, it's on this one. The Laplacian is performed with a 3x3 convolution with these weights that he gives us. So I'm actually going to use not a 3x3 convolution, but a 2x2 convolution. And what's the best way to illustrate that? 2x2 Laplace convolution. There you go. This is great. So let's do this. Okay, so this is a good diagram for how a Laplacian works. This is a 3x3. We're using a 2x2, but that's okay. So you can see basically that this is our source, and we have our grid of pixels. This 6 is the current pixel. What the Laplacian does is basically update the current value based on its neighbor values. In this way, you can think of it as a weighted average of neighbor pixels to update a current pixel value. That average is based on a convolution matrix, which basically defines the weights for each of the neighbors and how they are going to be composed together to arrive at a single value, which will be the new value of the destination pixel. So in this case, we take this 3, multiply it by the -1, add it to 0 times 0, add it to 1 times 1, add it to 2 minus 2, etc. And in this case, we will get a -3. Now, the weights are defined such that there are specific properties of the Laplacian. I'm not going to use these weights specifically because we're going to be using a 2x2. So we're basically going to be looking at the upper, lower, left, and right. And in our case, we're going to be taking the left, right, bottom, top. We're going to add all of those together. So you can imagine just ones on each of these. And then there's going to be a -4 in the center. And so we're going to subtract 4 from our sum, and in that way we're going to basically remove the effect of the current pixel and just take in the effects of our top, bottom, left, and right neighbors. So in this way we'll be averaging all of our textures, in this case concentrations, through the Laplacian filter, and that is what will give us the value for this Laplacian A component and Laplacian B component. So now let's get into TouchDesigner. I will reset this. We can see our system grow, and as I increase the number of passes, we can see that this system is growing pretty fast. We can play with the feed and kill rates. So by dragging this feed rate down, I'm changing the system quite a bit. I can change it more by changing these kill rates. and you can see that it is pretty sensitive to the initial conditions here. So I'll go back to my default, and so this is what we're going to be building. Now, I'm going to keep this, and we're just going to restart a new component, and this new component will be a container. I'm going to call this Gray Scott Tutorial, and we'll jump in here and start building our reaction. So the first thing that I'm going to do is just drop down a noise. This noise, I'm going to have a resolution parameter on my parent. I'm going to default this to 1920 by 1080, and then I'm going to set my noise to this resolution. I'm going to then make sure that it's a 16-bit float and my monochrome is off. So now I just have a noise. I'm going to also maybe take a speed parameter speed chop, and then translate this noise. Actually, no, I'm not going to use a speed to do that because this is going to be just our initial condition, so I'm actually just going to seed it with me.time.frame. So this thing is going to be updating like crazy, but I don't really care because this is just my initial condition. I'll drop an in right after that, and then we will have a null, and I'll call that null sim data. Then we're going to drop down a GLSL multi. I'm going to call that GLSL multi Gray Scott Reaction-Diffusion. Output this, and then actually before this null sim data, I'm going to add a feedback. And so this is going to give us our little simulation network. I'll drag and drop that null 1. Actually, maybe I'll call it null sim out, just like that. And there you go. So now I have a nice little feedback loop with this GLSL in the middle. Now this GLSL, we are going to need a few things, and I know that we're going to need a few things, so I'm just going to give them to us now. One is going to be a uniform called UDT. We'll need one called UFill, or UKill. We'll need one called UFeed. And I think, oh, and then we'll need U-diffusion A and U-diffusion B. And then last but not least, we'll need a mouse. We'll come back to the mouse, possibly in part 2, depending on how long this one takes. So now that we have kind of all of this set up, we can go into our shader and start to work in that. Actually, before we do that, I'm just going to go the whole way to our parent component, and I'm just going to add the parameters for this, because we might as well do that now while we're getting everything set up. So I'll have a parameter that's called kill rate, and we'll probably have to come back and change these mins and maxes in a second, but I'm going to have maybe 0 to 0.1 for my kill rate, and my feed rate the same, 0 to 0.1. And then as far as the default values go, actually this is something worth talking about. Because our initial conditions vary the results so much, people have done a lot of work looking at types of parameters that are going to work well together. So we have this, let's say f feed rate is 0.055, kill rate is 0.062 as a nice default value. So I'm just going to take that, my kill rate, which was 0.062, and then my feed rate 0.055. If you go through and read the rest of this tutorial materials from Carl Sims and from these other explorers, various resources that I've linked, you can get a better understanding of kind of the full breadth of complexity of these. And actually, Carl Sims also gives us a very nice tool where you can actually kind of click and drag here to see different feed and kill rate parameters. And using those different parameters, then you can kind of just like see how that changes the entire simulation. So part 2, we're going to talk about using these in presets, but for right now, I'm just going to grab a couple that seem right. And so now I have my kill rate, I have my feed rate. UDT, that is just going to be a 1. So for my diffusion rate A, be 0.0297, and diffusion rate B will be 0.105. And then my mouse, well, we don't really need my mouse right now. So now that we have those parameters set up and some sliders to drag, now we can really get into the Reaction-Diffusion shader part of this work. And so for that, I will open up my VS Code. And here we go. So we'll say this is a gray Scott Reaction-Diffusion shader implemented for TouchDesigner by Lake Hickman. Okay. So the first thing that we can do is just get our uniforms ready. So we can have a uniform float, UDT, ukill, ufeed, udif-A, and udif-B, and then a uniform vec3, umouse. I'm going to define my input textures, and here I'll define my input texture sim just with 0, meaning my first input. And then we can move down to our shader, and we can say vec4 sim data, grab our sim texture here, and then we can say vec4 color and just write that equal to sim data for right now. Now in TouchDesigner, we reset our feedback, and we can see that we are indeed just piping this right through. And so now, basically, what we have to do is in here, write output. So in here, we will implement Gray-Scott Reaction-Diffusion equations. So the first kind of step that we need to do there is going to be actually sampling our current value, sampling the neighbor values, and then getting that Laplacian function going. So let's jump into that and see where it takes us. So now that we're ready to begin implementing the shader, let's do a couple things just to give us some quality of life. So here we'll just define the texture channels. R equals concentration A, G equals concentration B. And then I'm going to change this, well, let's just start writing it. So first we need our sample. So I'm going to call that UV equals VUV.st. And then I'm actually going to get rid of this sim data, and so we'll just get that information again, because the first thing that we need to do is implement Laplacian step. And so the Laplacian, if we remember, is this, which I said we're going to use the coefficients 1, 1, 1, 1, and minus 4 to calculate the diffusion step. And so what that means is we need the left, right, top, and bottom values, and we're going to add all of those together and then multiply our current value by 4 and subtract that from the end. So the first thing that we can do is do a float step in our x direction, and that's going to be equal to utd output info.res.x, and this would be the width of texel in x direction, and then we'll have our float step y, which will equal utd output info.res.y, which will be the width of the texel in the y direction. This autocomplete that you're seeing is because I'm using Microsoft, or rather GitHub Copilot. I'm going to try to type everything out longhand anyway, but just in case you're wondering what's going on there, or if I forget and hit tab, that is, yeah, what the autocomplete is doing. So now that we have our step size, we can basically define a couple left text, and this will be VUV, or sorry, UV plus vec2, and then because it's our left, it'll be minus step in the x direction and then 0 in the y direction. Then we're gonna repeat this, and instead of left, we'll call it right, and that'll be a positive. And then we'll use our top text as the name and bottom text as that name for our top and bottom. And because we're doing our y, this will be plus vec2 0 and step y for the top, and then 0 and minus step y for the bottom. And then we can sample sim data using these texel chords. And so we're only going to grab the vec2 because we only want our R and G. So we can say vec2L equals texture std 2D inputs sim data, and then we'll use our left text chord and we'll grab the R and G components. Now we will do the same for our R and our T and our B for right, top, and bottom. And the only thing we should need to do here is replace our texture coordinates with the right text, top text, and bottom text. Now we can calculate the Laplacian. And for that, it'll be another vec2 Laplacian, and we'll set that equal to L plus R plus T plus B minus 4.0 times, and this is where we would have our current cell.rg, and that is actually something that we just need to recreate here. So vec2 current cell, and that'll be obviously using our texture std 2D inputs, and we'll grab the sim texture, which is defined up here as index 0, and then we'll use our UV and grab the RG components. Now this will allow us to kind of finish off this Laplacian term, and we can just jump back to our shader in TouchDesigner for a second to see if there's any data issues. We see that sim data is undeclared, and that's because I didn't update this kind of after we rejigged this a little bit into code. to fix this, I'm going to, instead of using frag color as my output, I'm going to add a layout, a location equals 0, out, vec4, and instead of calling it frag color, I'm going to call it osim. And then I will use osim down here, and what we want to do is output a vec4 that's going to have our, well, values that we have yet to calculate. But for right now, I'll just use the Laplacian, and then we can use 0 and 0 for the other terms. So now you can see we have no compile issues, and everything seems to be going well. If we reset our system, we can see, I mean, not really much is going on at the moment, and that's because we're not actually doing anything to our simulation data. But we're going to get to that in just a second. So now that we kind of have that Laplacian, we can actually move on to implementing the reaction-diffusion specific equations, which are going to be these guys. So we basically have our A and B, our current cell already. We need to compute these two terms, and then just add them multiplied by dt to our current to get our new. So we can say float dA equals Laplacian dot r times diffusion rate u diff a, just like that. And then we're going to actually just, I'm going to create another scalar quantity. I'll call it reaction, and this will be equal to my current cell dot r times current cell dot g times current cell dot g. And that's basically going to be my AB squared term. And so because of that, I can just simply, in my dA, write minus reaction, and that'll be this term right here, plus, and now I have my feed, u feed, right, times 1 minus my current cell dot r, which is my A concentration, and that's it. And then this will be calculate change in A concentration. And then we'll do the same thing for here. For B, we'll use our Laplacian G value times U diff B. This time we're adding the reaction. So we'll add that reaction, which again is this AB squared term. And this time we'll minus U kill plus U feed times our current cell dot G, and this will be our calc change in B concentration. And then we will update our concentration values from PDE result. And so I'll say vec2 new concentration equals current cell dot rg plus vec2 dA dB times ru dt. And now I'll just make sure that I'm outputting this new concentration. We'll go back to our shader. We'll see what these issues are. In line 40, current cell dot r, not dot f. That takes care of our compile issues. So now I can reset my simulation, and if I zoom in, we can see that this is indeed working. So our shader is pretty much set up, and the last thing that we need to do to kind of make this nice for an initial step is add some coloring. So to add coloring, we can, let's say, have a ramp. And I'll say one end of my ramp I'll make red, and the other end of my ramp I'll make blue. And we'll wire this into our GLSL. I'm going to hashtag define a palette texture that it will be 1. And remember, this is going to text replace palette with the integer 1 wherever it finds that. Colorize. Actually, I'm going to write the output up here. And what we're going to do actually for our colorization is define another color buffer so we can just output this color directly, although you could equivalently do this with something like a lookup. But I'm going to show you how to do it in GLSL. So we'll copy and paste this location. I'm going to change this to 1. This location is the color buffer. So this is saying color buffer 0 is going to take the vec4 OSIM, and then color buffer 1 will take another vec4, which I'll call OColor. If I go into my GLSL, onto the tab GLSL parameters, and increase my number of color buffers to 2, I can then use a render select, drag and drop my GLSL onto the top, and set the index to 1. This will then allow us to see that new color buffer, and we can see that by writing OColor equals td output swizzle, and then vec4 vuv.st, 0, 1. And this should just give us a nice UV map in our color buffer 1, which is what we see here. And so then to actually give us some color, we can do a float lookup, which will be equal to new concentration.r. And so we'll use the concentration of A to colorize. Then what do we need to do? We need to sample our palette. And so to do that, say vec4 color equals texture std 2d inputs. I'll use my palette macro. And then I'll create a vec2. I'll use my lookup and 0.05 as my x and y. And this will be color from palette texture. And then I can just release or replace this placeholder with a reference to the color that I just sampled from my palette. And now, if instead of viewing the simulation itself, we view the output, we can see that this is now nicely colorized. And of course, changing this value on my ramp is going to change. I can also very easily add new keys that are anything that we want, and so this can be used to really customizably color Reaction-Diffusion systems. Now, another thing that I want to mention is the number of passes that we're going to be running on here. I'm going to customize my parent component, and I'm going to use this passes parameter, which actually should just be set at 1. And you can see that the Reaction-Diffusion system is moving a lot slower if this is set at 1 by default. And then as we increase it to, let's say, 10, we can see the reaction increase in speed. So if I drag and drop this over and bind my new parameter as a master, I'll set the range max to like 100. And then if I open my parent parameters, we can use this passes to help control the rate of reaction. So as I drag the number of passes higher and reset my system, we can see the space is filled up much faster than if the passes were much lower, like let's say 6. This is moving at a much slower rate. So this can be another helpful way to increase the speed of the simulation, because we don't really want to increase this DT too much. If I do so, you'll see that we kind of just, well, end up with a unstable solution. So DT is not really meant to increase the speed of the simulation. To do that, we're going to use the number of passes. And so now we have this number of passes that we can iterate, and then we can also change the kill rate and the feed rate, and we can see that this leads to different dynamics just by doing this. Some of the solutions are stable, some are not at all, and so that's why it's helpful to have some of the presets that other people have already gone through the trouble of identifying and kind of just allow us to use some of those presets. So that's going to be the main topic of our next tutorial on this, where I'm going to take a lot of the presets from this WebGL Grayscott Explorer and basically turn them into a table that we can use to actually draw from, update our parameters, and save new presets if we want to. Beyond that, we'll be going into some second level usage of this, how to add interactivity, how to achieve some more complex types of patterns by using lookup maps and other sorts of multi-scale dynamics. And from there, I think it will be up to your imagination, which is really the only limit in this case. So I'm going to stop here. It's been a long one, a little bit more math than usual, but hopefully that wasn't too bad. I hope everybody is able to get this solution working. I'll make sure the files are up on Patreon, and I will also include in the YouTube description links to all of the resources that I have used so far in this tutorial. So with that said, thank you all so much for your support. I'm glad that you are tuning in and listening. The support through Patreon means a ton to me, lets me really do a lot more of this type of work, but also my own work than I would be able to otherwise. So thank you very much, and until next time, happy creating.